And so, welcome to our distinguished guest lunch speaker for the junior division of our virtual NC Science and Engineering Fair. Thank you for joining us. Today we have Dr. Rachel Lance, and I'm gonna get us started with just a little bit of information about Dr. Lance to get us going. And then I will pass the microphone over to Dr. Lance. Rachel Lance is an assistant consulting professor at Duke University Center for Hyperbaric Medicine and Environmental Physiology, where she investigates ways to keep human beings safe when they venture where they can't survive on their own. She holds a bachelor's and master's of science in biomedical engineering from the University of Michigan and a PhD in the same from Duke. She specializes in injury biomechanics, the study of injuries and traumas to the human body. Her scientific research covers undersea, high altitude, and outer space environments, as well as the mechanisms of injuries that occur in response to explosions. If you want to see Dr. Lance's extended bio, you can go back to Symposium. I do have a doc linked there with the rest of her information. So Dr. Lance, thank you so much for joining us. What I'm going to do now is stop sharing my screen and I will turn the spotlight on for you.
Great. Thank you for inviting me. This is exciting. So I do have a slide presentation that is just mostly pictures because what I do is really visual. So I've included a lot of pictures and a lot of videos to kind of give you guys the ability to imagine what this is like in real world science. But what I wanted to do is start with just a little bit of information about myself. Teresa gave me a great introduction, but basically I work at Duke University and there's a very specialized center there called the Center for Hyperbaric Medicine and Environmental Physiology. And basically what we do is we try to find ways to prevent injury and to prevent people from getting sick or having problems in environments where human beings aren't normally used to surviving. And the big ones that we cover are diving. So undersea, obviously people aren't really supposed to survive underwater. We're not naturally equipped for that, as well as things like high altitude mountaineering. We have frequently there worked with NASA, things like that. So people looking at going into outer space. And the reason that I love this work so much is because my favorite part of the human body is the lungs. Now, if you think about it, this organ is one of the most critical to our survival. You can live without food for 3 weeks, and you can live without water for 3 days. But if your lungs shut down and you can no longer breathe and get new oxygen, you've only got 3 minutes to survive. And so anytime you go into these extreme environments like underwater, where there's obviously no air to breathe, or high altitude, where there's less air to breathe, or even with blast trauma, where the lungs are the main organs that are going to be affected by an explosion, and I'll get back to that in a minute, that's where you have the most urgent need for finding a way to keep a person alive, because those lungs are impacted right away, and all of a sudden you only have a few minutes to live. So that's why I think this is a particularly exciting area of science. And it also brings in all these different topics. You have fluid mechanics, which is how I started out. I started with fluid mechanics study, looking at the way gas flows in and out. You have chemistry, looking at the way the blood carries the oxygen and looking at the way various drugs will affect the lung function. And you, of course, have lots of math as well. So one of the things that's really key about these different environments that I've listed is that things like underwater and things like high altitude, what you're doing there is you're changing the pressure that the person is existing at. So when you're going under the ocean, the pressure and the weight of the water on top of you increases the amount of pressure driving gases into your lungs, and it changes the way that your body takes in gas and processes gas. The opposite happens when you go to high altitude. So when you go to the top of a mountain, you're higher up in the atmosphere. There's less of the Earth's atmosphere pressing down on you. And that means you have the opposite problem. You have less pressure pushing oxygen into your body. And that creates a whole different host of problems. And the same thing, of course, is true with outer space, where astronauts in outer space are in this zero pressure environment. And there's no pressure pushing oxygen into their lungs. So we have to come up with suits and equipment and things like that to help them survive out there anyway. So what I'm going to do is start sharing my screen right now, because this is where the pictures start coming in. So don't worry, I'm going to make you read tons. This is supposed to be a fun event. So, but I wanted to give you kind of an idea of what I do and where I work and what that looks like as a scientist out in the real world. So this is just the talk of my slide, which Teresa already gave me a really great introduction, so this isn't really necessary. But one thing I want to emphasize here is that when there's not a pandemic, we love giving tours. I love giving tours. We have student groups in all the time. So once those regulations are back to what we normally do, I've included my contact information at the end of this. So if anyone wants to reach out through their school, things like that, we're always happy to host you and show you what this looks like in person and have you come to our lab. Okay, so this is a view of the hyperbaric chamber. And what a hyperbaric chamber is you can figure that out based on breaking down the word. Hyper is the prefix meaning high. So for example, like hyperactivity means hyper high activity. And baric is the word in Latin that means pressure. So together you see high pressure. Our chambers at Duke are really special because they're both hyperbaric, high pressure, and hypobaric. Hypo means low. So using what you see in this picture, which is the control dashboard in the front, that's how we have all of our gauges. We know exactly what's happening. And the chambers are in blue, and those are the big cylinders in the rear. We can take those chambers and either increase the pressure inside them or decrease the pressure inside them. And what that means is now we can simulate what's happening to people when they go underwater or when they climb to the top of a mountain or go into outer space. And that's obviously very convenient because we can do this all from inside the Duke Hospital. And so any given day at Duke, we have these chambers that are running and we have people inside and we have people at the outside seated at these controls. And yes, the buttons are very fun to push. And we can take these chambers either below the ocean or high altitude and use that to conduct scientific experiments to see what's happening to the human body when that's occurring and what we need to do or change in order to make that a more survivable situation and a more survivable environment for people through science. And so what I'm going to do is do just like a little bit of a virtual tour. Originally, my plan was to kind of bring you on webcam, but unfortunately, my husband had an accident and needs some surgery. So he's doing well, but I didn't want to leave him for that length of time to go into work today. So I'm put together just like a little virtual tour. So on the left, we see this red arrow, and that's kind of where we're looking in the lower right. So if you walk to the left side of the chamber and you look in, that's what one of those entry doors looks like. That's our first chamber. We have 7 in total. So this is one of the biggest complexes in the world. So 7 hyperbaric chambers makes Duke, which is lucky because we have this right here in North Carolina, one of the biggest and most impressive hyperbaric chamber complexes in the entire world. And that's why we get groups from all over the world coming to us to conduct research. We've had the Italian Navy, we've had the Australian Navy, we've had groups and people from all over the world who are interested in using our chamber for research. And that leads to a lot of really fun collaborations. So you can see here, one of the first things you'll notice in the lower right is how big and heavy these doors are. And this gives you kind of an idea. You can see like the thickness of this door. These chambers and their doors are solid steel. And because you have pressure inside pushing out, or when you go to low pressure, you have pressure outside pushing in, this is the thickness of the material that's required to contain that safely. It's kind of like being inside a giant scuba tank. So if you walked through that door and you kept going through those long tubes, this is what you would eventually get to. This is what's called Charlie chamber. This is our best, or not our best, it might be our best, but this is definitely our biggest chamber. And this one is just a giant sphere. So you're kind of in this huge steel balloon when you're inside Charlie chamber. One of the things that I think is really fascinating about this chamber is that it was originally built so that people could go in here and perform open heart surgery. Now, the reason for that is because this was built in the 1960s. And at that time, they didn't have a way to keep people's blood flowing past their lungs. Now they can do that. There's a machine called the heart lung bypass machine, and it'll push the blood around your body for you, and it will oxygenate it. Remember, you only have that 3 minutes to survive. So, but this machine creates kind of an artificial setup to keep giving you oxygen. Before that was invented, they wanted to use going to high pressure as a substitute. Okay, so if on the surface you only have 3 minutes to survive without oxygen, that's not long enough for surgeons to conduct heart surgery. So if you pressurize it, again, you're forcing more oxygen into the body. Now you've extended the length of time. So the idea was, if they built this giant metal ball and they conducted heart surgery inside this giant metal ball, they would be able to force more oxygen into the patient's bodies and give themselves like 10 or 15 minutes, except rather than 3. Now, what's kind of funny is that this chamber was completed the same year that bypass machine was invented. So it's actually never, ever been used for that. So it's never had heart surgery performed inside it, even though it's the reason this whole complex was built. But now we use it for other reasons. So for example, one of the major problems that we see is carbon monoxide poisoning, which you might have heard of. This is a thing that can happen if people are in the garage with the car running, or if people bring a generator inside the home. Those are really dangerous situations because they make carbon monoxide, which can deprive your body of oxygen. And so to fix that, we put them inside this hyperbaric chamber, which again forces more oxygen in. So that's kind of the common theme here. Okay, so that's the medical side of what we do. I'm on the research side. I'm a PhD in biomedical engineering, and what that means is that I conduct research. So I'm usually working with people who are healthy and who come in looking for ways to improve their performance on top of a mountain or stay underwater for longer safely, things like that. So we're going to go back out to the outside of the chamber, and I'm going to walk you in through the red arrow on the right. This is the experimental half. The left half is medicine and the right half is experimentation. So when we get in here, this is what it looks like. So you'll notice this is a lot less tidy than the other chambers. Immediately there are wires everywhere. And that's because we have 5 different scientists who all use this chamber at the same, not at the exact same time, but we're all sharing. This is a really unique resource. And so these are all the wires and cables and instruments that it takes to conduct science in these environments. And we have the experimental setups for all of our experiments going at any given time. And then once the experiment ends, we clean it all up. But we also have this water tank in this one. And that's where I personally love to do research. Because when you put someone in this water tank and then you pressurize the whole chamber around them, you've now completely simulated what it's like to take that person to 60 feet under the bottom of the ocean, 300 feet under the bottom of the ocean, 1,000 feet under the bottom of the ocean, if we really want to, all while we're safely inside the hospital, and they can come out of the water at any time they want to if they don't feel okay. So here's a test subject in there. I've blacked out their face because every time we use a human test subject, we keep that anonymous. So these are volunteers who come in for my experiments, and they let me use them for science, which is really fun. And it's actually how I also got started at Duke. So here's another experiment. This is one that I recently completed. And what this is showing is that same water tank. And this is a new type of breathing apparatus. So obviously when we're underwater, unfortunately, we can't just be like the fish, right? We can't just process the water through our gills. We have to carry the gas with us somehow. So this is a device that brings down the gas with you and you can breathe through it and you breathe it in a loop. So you rebreathe the same gas over and over and over again. And the machine takes out the carbon dioxide for you and adds more oxygen. So what we were doing with this experiment is we intentionally broke that machine and we were looking to see if I could come up with a way to create a safety device to warn divers that the machine was broken and that they were going to lose consciousness or pass out because they didn't have enough oxygen. So you can see here too, this isn't like normal diving. And this is why it's so much more convenient to do it in a chamber instead of in the real ocean. Because when we have people doing these experiments, we need to have wires on them. We need to have EKGs on them. We're monitoring their bodily functions to keep this as safe as possible. And that would be a lot harder to do if we were actually in the real ocean. So that's why this is such a valuable tool. So I wanted to pepper this a little bit with just a story about like kind of how I got started, because I think that one of the important things is that there are many routes to becoming a scientist. So some people start with more traditional ways where they start with college and then they go to grad school and then they get a job. And that's great, but that's not what happened for me. And so I think it's important to recognize that at least for my life story, the key to ending up where I am, where I'm doing what I love, and this is absolutely my dream job, has been just being really flexible and being able to take changes as they came and being able to pursue science when it came up as an opportunity. So this is a picture of my first chamber ever. This is the Hyperbaric chamber on Catalina Island, which is off the coast of Southern California. And so this is a desert island. It's only got about 3,000 people living on it, and it's a privately owned island. So they really, really regulate who can live there and why. And one of the things that's cool about this island is they have this hyperbaric chamber there. So it is run by the University of Southern California, but they allow any volunteers to just show up and live on the island as long as they're working at the hyperbaric chamber, where we would treat diving accidents. So if divers came to the surface too quickly and they got very seriously injured by that change in pressure, they would come to us and we would repressurize them and then bring them to the surface more slowly. So, and safely. So the reason I ended up there was, because when I was in college, I got really sick. So I had a heart problem. And at the time, I thought that was kind of the end of my scientific career. I thought that was going to be disabling enough that I wouldn't be able to work full time in a lab and do what I needed to do. And so I kind of just took time off and did what I needed to do and went and did science on this island. And it was peaceful. And I learned so much by doing these actual treatments. And it ended up spiraling into my current career. So to me, that's a really important story because I don't think a lot of people talk about the times in their life when they think they've failed. And for me at that point, I thought I'd failed, but it ended up just being a different window to a totally different opportunity and a new career that I'd never really thought of before. So chambers will always have a special place in my heart. Okay. So what I want to talk about next is another extreme environment. We've talked about undersea, we've talked about outer space. So I'm going to talk about explosions. This is also pressure changes. And the reason that explosions, I don't need to explain why explosions are fun. You guys already understand that. So here's a picture of a movie. And I didn't want to pick on this movie in particular, but it does represent something that happens a lot in movies. You see these guys being thrown. See, everyone's just being tossed all over the place. There's these big fireballs. I'll play it again. There's these big fireballs. Oh, everybody's getting thrown across the room. And this is common. This happens all the time in the movies. And what I really want to talk about here is how that's not a realistic portrayal of what an explosion is and why that matters. Okay, so we're going to bring in our science just a little bit. It is a science fair. So we're going to talk about density. And the way that we know that density can cause an explosive injury. So here's an animation, and this is obviously an animation, but it is accurate. And when you have a solid material or a material that's more dense, any pressure wave, so like an explosive pressure wave or even sound, will move faster through that dense material than it will move through the less dense material like gas. And that's because these molecules are closer together, and so they ricochet into each other more quickly. And that ends up transmitting that pressure wave faster. So the real world example I really like to use is whale sounds. So if you think about whales and whales singing, you can hear whales singing in the water for miles and miles away. And obviously that's not really possible in the air. And the reason for that difference is because of that change in density. When you increase the density from air to water, you're increasing how easy it is for those sounds to transmit. So they go faster and they go farther because it's so much easier to transmit. Okay, so that's our little like science break. That's the physics behind blast injuries. And so what I'm going to show you here is an x-ray. So this is an x-ray of the lungs. Again, these are my favorite organs. And so when you have a normal lung on the left, the x-rays usually go straight through. They black on a lung x-ray is good. It's good. You want to see black. You want to see that these x-rays have gone straight through and these lungs are clear and they're full of oxygen and they're delivering that oxygen to the body and it's beautiful. So what happens with an explosion, now we've talked about density, we've talked about the lungs being full of air. So connect those two concepts together, right? If the body is mostly water and the lungs are mostly air, what happens is it moves through the body really quickly and easily. And then it hits the air where all of a sudden it has to slow down. And it's kind of like it's hit a wall. So this pressure wave is then causing problems at the surface of the lungs because it's being forced to slow at that change in density. So, and there's no quiz on this, but hopefully that made sense to everybody. I tried to include as many pictures as I can. So on the right, you have an x-ray of someone who's been exposed to an explosion. And you can see here now where the arrows are pointing, all of a sudden their lungs aren't black anymore. The x-rays aren't going through. So you can see where that damage has occurred, where they had the wave that had to slow down because of that change in density. And so this is one of kind of the take homes with me and my particular academic background. A lot of this started just because I really love fluid mechanics. And I honestly didn't know what I was going to do with it. I just thought it was fascinating. I was like, this is how you predict things moving through pipes. But then all of a sudden, when you get out to the real world, these principles and these concepts apply to the way gas flows through the lungs. They apply to the way blast pressures move through the air. They apply to the way the explosion occurs itself, which I'm not going to get into today because that's a little bit much for this length of time. But so all of a sudden, that for me was the biggest moment in my career as a scientist, was the first time that I started taking some of these abstract principles that I learned in school, which like you don't always see how it applies right away. And then I started having to apply them to some of these real world problems. Okay, so the next one I'm going to show you is a real explosion. Okay, so this is a real explosion. This is a real video. This is an explosive called C4, and this is very commonly used by both our military and other militaries around the world. So you can't see the actual explosive material. It's out of the frame. That's just the limitation of these high-speed cameras. But you see the fireball it's making, which is really cool. So, and you can also, if you watch closely, you can see the pressure rate. So the pressure wave goes and it hits this dummy before the fireball comes. So you just saw it go past and you could see like kind of his clothing is rippling and he's got like the little squirt things blown off. So it just hit him again. So the important thing here is that this dummy is not attached to the ground. So this is what a real explosive looks like. So you go back to the movie ones where everyone's being thrown around. That's not actually realistic because these things happen so fast that there's not enough time to accelerate the body like that. So again, this is when you're starting to get into your physics, you're starting to get into your kinematic equations that you guys will hopefully stick with science and learn through high school, and you'll be able to calculate this stuff for yourselves. But for now, this is just looking at the reason that explosives are a problem is because of that density change we talked about, and because they affect the lungs. And so again, this all comes back to the lungs. This all comes back to survival and breathing gas and how we process breathing gas. And the fact that when this person gets hit by the explosive, all of a sudden they have less than 3 minutes before they have a serious problem because their lungs are so damaged that now they're no longer processing oxygen. So, okay, a little bit of the lighter side. So explosives make shock waves, and that's a very specific type of pressure wave. But I wanted to kind of tie this back into more real world scenarios that you guys will be able to relate to. So you're never going to be able to look at party balloons again the same way. It's going to be so much more fun for you now because you'll be able to tell people that when you pop a party balloon, you have just made a shock wave. So it is exactly the same as an actual explosion. So if you had taken C4 or TNT, you've just done the same thing with your party balloon, except you've done it on a much, much smaller scale. Obviously, party balloons are not going to hurt anyone. So it's kind of like, my dog was just pawing at the door. So it's kind of like if my dog ate one M&M, she's fine. If she ate bags and bags of M&Ms, she would not be okay because dogs can't have chocolate. But so these party balloons, what they do is when you create this high pressure area and then they pop, you get the same kind of pressure waveform that propagates outward as you do when an explosive goes off and it creates a pressure waveform that propagates outward. So when you hear a Mylar balloon pop, you are hearing the sound of a small explosion. And I think that's really fun because, again, this is how we simulate it in the lab. So if I'm in the lab and I want to simulate an explosion and I want to set up all my pressure gauges and see what's happening, I don't go get a block of C4. That's like it's a lot of work and it's a lot of permits that are required and it's less safe. What I do is I take tons of Mylar and I pressurize the Mylar until the Mylar pops. And so it's the exact same material as these party balloons. So another one I hope you never ever encounter is a volcano, but volcanoes do the same thing. So you think of it as an eruption, they also create a shock wave. So anytime you get this pressure release, you're getting the same thing as this explosion, and it's all pressure and it's all dangerous because of the way that it can affect the lungs. So okay, so now what I'm going to do is tell you a brief story about one particular explosion. And so this is kind of my example of how you take all this theory and you turn it into something else that works for you in a career. And it will also explain, finally, this big white thing behind me. So, okay, so this is an explosion that occurred on February 17th, 1864. So those of you who have paid attention in history class will know 1864 in America is the tail end of the American Civil War. So this is an explosion that occurred as part of the American Civil War, and it occurred in the water outside of Charleston, South Carolina. What was happening there is the Union ships had all kind of swarmed around Charleston, and they were making a blockade, and they were trying to prevent any of the foreign countries from bringing in water or not water, materials or supplies or food. And so the people of Charleston wanted to eliminate that blockade and get rid of it, obviously. So this is a picture of the explosion that occurred. The Confederate military tried to blow up a specific boat called the USS Housatonic, and they were successful. And they were trying to do that to break the blockade. So the way that they did it was they built a homemade submarine. This is definitely a do not try this at home type moment. But for them, they were desperate. They didn't have any food. They didn't have any supplies. They're being blockaded by these ships. And so they built this ship, this little submarine, out of scrap metal and bits and pieces that they could find within their states that were trying to secede. So this is the submarine H.L. Hunley, and it was about 40 feet long, and it was about 4 feet in diameter. So if you can imagine that, that's about the length from the tip of my hand to about right here. So it's not very big. It's really cramped. And what's impressive about this submarine is that it was powered by hand. So there were 8 people inside total, and 7 of them cranked a hand crank in order to move that propeller. February 17, 1864, was when those crewmen took the H.L. Henley, cranked it out into Charleston Harbor, and used it to press a black powder bomb against the side of the USS Housatonic and sink it to the floor of the ocean. Okay, so why do we care all this today? This is just a bunch of people in the Civil War, right? Well, this is an interesting problem from a scientific perspective because the Hunley was recovered in the year 2000. So here's a picture of that actually happening. Most of you were not alive at that time, but I was at least not aware of this event because I was a teenager when it was happening. And I didn't necessarily care about Civil War submarines at that point in my life. But anyway, they brought it up and they brought it to a lab in Charleston, South Carolina, because after its successful attack in 1864, it had disappeared. Nobody ever saw it again. It just floated away. They never came home. Nobody knew what happened. So they brought it up to this lab in 2000, and they were hoping that this would kind of help solve the mystery of why this submarine disappeared so long ago. Why did this crew never come home? And one of the things that they found when they started opening the submarine and pulling all the silt out and pulling all the artifacts and mapping where it all was, which is a whole different subset of science, right? So archaeology, these people were using precise calculations of where everything was located in the boat, and we're putting it together like a crime scene. How did this piece fit? Where was this guy sitting? What was the damage shown? How did the patterns of the soil indicate what had happened in 1864? And as they pulled out bit and chunk and piece, what they discovered was that each of the 8 crewmen were still inside the boat when it sank, and they were also still seated at their battle stations. Nobody had tried to get out. Nobody had any signs of injury, and nobody had any remaining skeletal trauma. This is a computer model that a friend of mine has made. And so this is the pilot of the submarine. So what you're looking at is the side of the submarine as if one of these panels had been removed. And this guy, and this, he's got a bar that's kind of sticking up between his legs. That's how he would have steered the submarine. And he's sitting at like a little table where he had all of his instruments, and he's sitting on his own bench. So you can see kind of his shoes there and his leg bones leaning back, and then the other bones are his arms. And so what this shows, these are how his remains were actually found. So this guy is directly below the exit from the boat. He just needs to stand up and he's out in the air and freedom. And he is instead just slumped over on his little bench. So this is scientifically fascinating. This is a really interesting question. And so one of the other things that came up was that this is the end of the spar that had used to press the bomb against the side of the ship. And you see here the copper shards. So this looks just like a Looney Tunes cartoon, right? So this is like fully exploded. These are the shards that have been pulled back and peeled open as it exploded. And that's exactly what happened. Now, what that means, if you think back to the video of the guy in the real explosion, where those blasts are not really moving people, we now have all of the equations that we need to do the math to figure out how much blast they would have been exposed to inside the submarine, because we know the spar, we know how long the spar was, we know how big their charge was, and we know where they were sitting. And so that turned into kind of an experiment that eventually became part of my doctoral dissertation. So my doctoral dissertation is in injury biomechanics. But I specialize on the way people are injured by explosions. It is my favorite thing to study, in addition to other extreme environments. So this is kind of an example of what real science looks like. Sometimes real science gets ugly. And so this is me in the pool of an apartment complex. It was nice enough to let me test my model. We built a 1/6 scale model to replicate the explosive and the submarine, and Duke was nice enough to let me use their water pond for part of it. So I'm wearing so much clothes there because the fish in that pond were biting me. Just trying to avoid fish bites. And this was a really hot day. And then we also worked with the Department of Alcohol, Tobacco, Firearms, and Explosives, which is abbreviated the ATF. And they came and were on site for some of our testing. So I got to build real black powder bombs. And so I got to build real charges and set them off and measure what happened in the water and inside my model submarine. So the reason that I show this picture is just show that you could have a theory, but as you guys know, because you are science fair participants, and so you are already so many steps ahead of the rest of the world in understanding this, it does not matter what you think or what you feel until you get data for it. That's real science, right? Like you need to get the facts and the numbers, and you need to set up your experiment, which I'm really excited you guys have all been doing. And this is what we do in the real world as well. And sometimes if we're lucky, that involves explosives, as long as we do it safely. The other
Dr.
point
Lance?
of, so yeah.
I'm sorry. We just have a couple minutes left. So
Okay,
I want
great.
to give you
So
a heads
this
up.
is the end anyway. This is the end. The other point was that this is me and my team. Nobody does this alone. So projects and teamwork are, so this is it. That's the end. And then there's just a video of an explosion. Okay, I'm gonna go ahead and stop sharing, and I guess that's time for questions.
Yes, I love it. So, kiddos, we only have time for like 1 or 2 questions if you have them, and I'm happy to get it started. So, Rachel, as you talk to us, first of all, I'm totally fascinated. So, thank you for bringing in so much for us to kind of understand the science and the experiment. Um, One of the things my brain goes to as you're talking, and actually, if you look at, I don't know if you can see the chat or the participant group, but there's a lot of physics and mathematics and technology students in here. And I just wanted to hear you talk a little bit about your degree is in biomedical engineering, but you are clearly using a lot of disciplines in your work.
My degree is in biomedical engineering. That degree is fairly vague. So biomedical engineering can mean everything from doing cell culture stuff to doing larger scale stuff like I do. And it's basically how human beings interact with the world around them. So that's why it's very vague. We interact with the world in a lot of ways. So people who do physics or engineering, I actually started out studying mostly mechanical engineering. And so that's how I got into fluid mechanics. That a solid foundation of physics is going to let you jump into any area of science that you want. So if you get that solid foundation in physics and math, I don't personally think there's a need to decide what you want to do right away. I kind of took what I call a random walk, which is a biology joke. Yeah, nobody ever gets it. I took kind of a random walk, but once you get that solid foundation of physics and math, you'll find that you're qualified to learn any specific area of science that you want. So,
That's awesome.
Yeah.
Great. And I'm just going to throw it out there. Do we have any specific questions for Dr. Lance before we shift to our next presentation? And Dr. Lance, if you would, I know you said you have contact information. Can you drop that in the chat for these folks? And while you do that, I will just grab my screen again. And on behalf of the Science Fair Foundation and all the students that were able to attend live today and those that will get to watch this in the recorded form, we just want to really express our appreciation. The talk just really has been stimulating, but it also pushes our thinking about what biomedical engineering is, what all the career and collaboration requirements are under it, and also that pathway to feeling good about the work you do. So truly, truly appreciate you jumping in and sharing your story with us.
Oh, and someone say, what's the best part of your job? I'd really like to answer that one.
Oh, go right
Um,
ahead. Yes.
the best part of my job is when I get a piece of data that works for the first time. I think that that is the moment that drives us all in science. Science is a lot of patience and a lot of frustration and a lot of failure until you manage to get that first piece of data where your experiment works for the first time and you just have this yes moment every single time. And that is the absolute best part of my job. So
That is awesome. Yes, and I apologize. When you start sharing your screen, the chat like gets whisked away.
I found it again.
That's awesome. Oh,
So,
fantastic. All
okay.
right.
But
So
yeah, like I said, I put my contact information in there if anyone wants. Things are difficult with the pandemic now, but normally we do love giving tours, and I'm happy to do that anytime once the hospital lifts the visitor restrictions. So,
that's fantastic. I'm definitely going to be reaching out to you.
okay.
To bring groups of students. So for those of you who were able to participate live, I just want to remind you that at 12:15, we're going to start 2 minutes with a mic, which many of you are participating in. And Dr. Lynch, just so you know, that is the students presenting their research for the public. So they'll get 2-minute summaries.
Yeah. Yeah. Like to stick
Wonderful.
around.
Well, thank you all so much. I dropped that link in the chat, or you can grab it from Symposium. Have